All right, welcome to this explainer. Today, we're going to completely dismantle how you measure, think about, and talk about system performance. If you've ever stared at a monitoring dashboard and thought, hey, everything looks fine, while your users are actively blowing up your inbox complaining that the system is incredibly slow, well, you are exactly in the right place.
So I want you to ask yourself a really honest question. Is your system actually fast, or is it just fast on average? We rely so heavily on these dashboards that show us big, friendly green numbers based on averages. But here's the hard truth. Those averages, they're likely lying to you about what your users are actually experiencing on the ground. Averages completely hide the extremes. Think about it. If one user gets a response in 10 milliseconds, and another user is sitting there waiting 10 whole seconds, the average might still look perfectly acceptable. But that second user, yeah, they are likely never coming back. So today, we're going to challenge this myth of the average and give you the real mathematical tools you need to accurately describe performance.
Okay, here's our roadmap for the explainer. We'll start with number 1, the myth of average speed. Then 2, latency versus response time. Next, 3, understanding queuing delays. Then we're going to get into 4, measuring with percentiles. 5, tail latency amplification. And finally, we'll wrap the whole thing up with 6, SLAs, SLOs, and impact.
Let's jump right in. Section 1, the myth of average speed and why averages lie. To accurately understand performance, we first have to isolate two absolutely crucial concepts. We've got response time and we've got throughput. So response time is the elapsed time from the exact millisecond a user makes a request until they receive the completely formulated answer. It's the end-to-end measurement of the user's wait. Throughput, on the other hand, is the number of requests per second, or the data volume per second, that the system can actively process at any given time. Now, what's truly interesting here is how different the impact of each metric is. Throughput dictates your hardware cost, right? It tells you how many servers you need to provision, what your network bandwidth limits are, how your database is going to scale under heavy load. But response time, that is the metric your users actually feel. You could have a system with incredibly high throughput, processing thousands of transactions a second, but if the response time for an individual transaction is 5 seconds, your users are going to perceive the system as completely broken.
Moving right along. Section 2, latency versus response time. Let's look at the journey. Let's trace the actual physical journey of a single request here. Imagine time flowing from left to right. The client makes a request and it travels across the network. That initial transit time, that's your network latency. Then it hits the service, but the service doesn't process it instantly, right? It almost always sits in a queue waiting its turn, so that's your queuing delay. Only after waiting do we hit the actual service time. That's the duration the service is actively using the CPU or reading from the disk to process the request. Finally, a response is formulated, it queues up again, and it travels back over the network. The total response time is that entire measurable window the client experiences. It captures absolutely all of these individual delays, all mashed up into one final number.
Now, latency and response time are thrown around interchangeably in the industry all the time, but honestly, they strictly shouldn't be. Latency is a catch-all term for the time during which a request is not being actively processed. It is latent. It's waiting. Network delay as packets hop between physical routers. That's latency. Sitting in a TCP buffer? Latency. Waiting for a thread pool to free up? You guessed it, latency. It is an entirely separate concept from the actual service time used to execute the code. So, rule of thumb, when you hear latency, I want you to think waiting. When you hear response time, think of the total round trip.
Section 3, understanding queuing delays, which is usually our biggest bottleneck.
So a server can only process a small number of things in parallel. It's limited largely by its number of CPU cores and available execution threads. What happens when a highly loaded system gets a really complex, slow request? We get what's called head-of-line blocking. Think of it exactly like a grocery store checkout lane. If the person at the front of the line has a cart completely full of pennies and some complicated coupon dispute, it really doesn't matter if everyone behind them just has a single loaf of bread. The whole line grinds to a halt. In a computing environment, a single heavy database query or a super slow external API call can monopolize an entire worker thread, and then subsequent, potentially very fast requests get stuck right behind it, causing massive queuing delays for everyone trapped in that pipeline.
And that dynamic creates this infamous hockey stick curve of queuing delays. Take a look at this. On the horizontal axis, throughput increases, gradually approaching the maximum capacity the hardware can physically handle. On the vertical axis, we're measuring response time. Notice how the service maintains a nice, low, flat response time when the load is light. The queues are basically empty, so requests are processed almost immediately. But as throughput approaches capacity, the response time doesn't just tick up a little bit linearly. No, it skyrockets dramatically. Because the CPU is already incredibly busy handling earlier requests, incoming requests are forced to wait longer and longer in the queue. At these high percentiles of utilization, even tiny little fluctuations in incoming traffic cause exponential increases in wait times.
And it gets worse. If you push throughput too close to that limit, you risk triggering a metastable failure. Basically, when a queue gets excessively long, response times increase so much that client applications start hitting their predefined timeouts. And what do automated clients do when a request times out? Well, they retry the request. Now, not only is your server struggling to process the original backlog, but it is actively being slammed by duplicate requests from impatient clients. This artificially inflates the request rate even further, creating a phenomenon known as a retry storm. Your system becomes completely bogged down doing redundant work, often processing requests where the client has literally already given up and closed the connection. It's a vicious cycle of overload, and honestly, the system will often just stay in this failed, unresponsive state until you forcefully throttle it or manually reboot it.
All right, Section 4, Measuring with Percentiles. This is the core math we need. When you plot a sample of, say, 100 requests, where each gray bar here is a distinct request and its height is the duration, the limitations of averages become staring you in the face obvious. See that solid horizontal line labeled mean? That's your arithmetic average. It doesn't tell you much at all about the typical user experience because it's heavily skewed by those massive occasional outliers spiking way up. And outliers happen in computing constantly. Garbage collection pauses, network packet loss, brief moments of CPU contention. Because these spikes are phenomenally large, they drag the average up, making it a mathematically meaningless metric for understanding what a normal user actually feels. To know the typical user experience, you've got to take your list of response times, sort them from fastest to slowest, and look at the percentiles, which are those dashed lines you see there. To evaluate performance accurately, you need to break down these specific metrics. Literally, ignore the mean entirely for user-facing experience. Start with the P50. This is also known as the median. If your P50 is 200 milliseconds, exactly half your requests are faster than that and half are slower. It perfectly represents your typical wait time. But to figure out how bad your outliers are, you've got to look at the higher percentiles, the P95 and the P99. A P95 of 1.5 seconds means 95 out of 100 requests are faster, but 5 out of 100 users are suffering a painful wait of 1.5 seconds or worse. And then the P99? That isolates the absolute worst 1% of requests. It reveals the true tail latency outliers that drive your users away. Now, you might be wondering, why on earth should I dedicate massive engineering resources just to optimize for 1 out of 100 or 1 out of 1,000 users? Well, Amazon provides a totally perfect example of why. They measure their internal service response times not at the average, but at the 99.9th percentile. Why do they do that? Because the customers experiencing those painfully slow outliers are very often the ones who have the most data on their accounts. They have the most data because they've made the most purchases, uploaded the most files, or interacted the most with the platform. Basically, your slowest requests are disproportionately hitting your most valuable power user customers. Keeping tail latencies low is quite literally about protecting your highest revenue, data-heavy users from a terrible experience.
Which brings us to Section 5, Tail Latency Amplification. This is the climax of why this all matters.
When an end user makes a single request to a modern web application today, that app almost never handles the request all by itself. Instead, it fans out. It makes multiple parallel calls to various backend microservices. Now, if it makes, let's say, 7 backend calls, even if they're fired off at the exact same time in parallel, that end-user request still has to wait for the absolute slowest of those calls to finish before it can render the final page. If backend number 6 hits a P99 delay of 487 milliseconds because of some temporary queue spike, the entire user experience is dragged down to 487 milliseconds. And this is where the math gets absolutely brutal. Because you're basically rolling the dice multiple times per user request, the probability of getting a slow backend call increases drastically. Think about it. If a single backend service has a P99 of 1 second, that means there's a 1% chance a single call takes a second. But if your user request fans out to 100 backend services, the mathematical probability that at least one of those calls takes a second jumps to roughly 63%. You have just amplified a rare 1% anomaly into a common, everyday performance failure that hits over half your users. That is tail latency amplification. Just one single slow sub-request ruins the whole shebang.
Section 6. SLAs, SLOs, and impact. Let's see how we apply this math in the real world.
We operationalize all this math through SLOs and SLAs. Service Level Objectives, or SLOs, are the internal targets your engineering team sets for expected performance. For example, an SLO might dictate that your checkout service has to maintain a median response time under 200 milliseconds and a P99 under 1 second. It gives you a concrete threshold for when performance degrades enough to warrant jumping into an incident response. On the flip side, Service Level Agreements, or SLAs, are the actual formal, legally binding contracts with your clients. They spell out exactly what happens when you consistently fail to meet those objective targets. Violating an SLA isn't just an engineering problem, it triggers serious business impacts. We're talking mandatory financial refunds to enterprise customers, losing contract renewals, and suffering massive reputational damage. Truly understanding percentiles is the absolute mathematical foundation of writing, monitoring, and ultimately surviving these operational agreements.
All right, let's do a quick summary of the core takeaways we've unpacked in this explainer. First off, averages mask the true user experience. Because outliers drag the math heavily, you've got to stop relying on averages for user-facing metrics. Second, keep those strict definitions in mind. Latency is the time a request spends waiting in transit or in buffers, whereas response time is the total round trip that the client actually sees. Third, beware the queue. Queues cause those terrifying hockey stick delays under load, and head-of-line blocking can cripple an entire CPU just because of one heavy request. Fourth, you absolutely must use percentiles like the P50 and P99. They actually reflect reality, showing you both the typical user experience and those worst-case outliers. And finally, never forget the danger of tail latency amplification. Because modern architectures fan out requests, a slow P99 on a single backend database doesn't stay isolated. It exponentially ruins the entire parallel user experience.
So I want to leave you with one final, kind of provocative thought. What are your P99 users experiencing right now? The very next time you open up your system monitoring dashboard and you see this beautiful low average response time, I want you to dig deeper. Find the percentiles, investigate those tail latencies, because buried right there in that P99 might just be your most valuable customers, frustrated and waiting in a queue. Thanks so much for joining me on this explainer. I really hope this helps you build faster, more resilient systems.